I welcome respected speaker Dr. Amit Kumar Mishra, Head Department of Computer Science and Engineering, Sagar Institute of Science and Technology, Bhopal. Very warm welcome, sir, and
Thank you,
over to
ma'am.
you, sir.
So, hope I'm audible to everyone.
I welcome respected speaker Dr. Amit Kumar Mishra, Head Department of Computer Science and Engineering.
Shall I continue, ma'am?
Yes, sir.
Yes, sir.
Okay, thank you, ma'am. Actually, कुछ voice बीच में repeat करना
हाँ
चालू
हाँ
करेंगे.
Yes, sir.
So, good morning, everyone. This is Dr. Amit. Actually, here I'm going to talk about the quantum computing. And as ma'am already said about me, I'm a head of the department at SISTEC Gandhinagar Bhopal campus. And here I'm looking after the machine learning and deep learning, basically. So before going to start my talk, I'd like to give you discuss one thought of John from Cisco Systems. So he said that at least 40% of all businesses will die in the next 40 years if they don't figure out how to change their entire company to accommodate new technologies. So basically, what it means, what is the role of technology in our life, that I would like to discuss here. And then slowly I'll go ahead and I will talk about the quantum computing and quantum computer itself. So here I'm going to give you some idea about the top 10 global companies in the sense of their capitalization from March 2022 report. It is there. So you can see these are the top 10 companies in the market. Out of these top 10 companies in the market, you can see more than 50% of companies, they belongs to the technology itself. They work on the technology. You can see this much of market capitalization, they place their role into the market. So, what is the scenario of top CEO of, in the global scenario? If you see the top global trends which CEOs believe will transform their business over the next 5 years, that is the technology itself. You can see here the more than 77% of CEOs, they feel that that would be a percentage of role in their company growth. Means technology will help out them to grow their company basically. So if I'll tell you what are the top 6 emerging technologies leading trend, if I'll show you here, the trend and the innovation that will save the technology industry over the next several years are coming into the sharper focus. This is the report of Forbes. This is a very well popular magazine over the world. You might be knowing about it. So out of all those, my focus is on the ubiquitous computing, and inside this, I have a topic that is the quantum computing. This is the most emerging and latest field in which people are going to start working upon in India. Basically, other countries they have already started to work upon, and here we have started in India to work on the quantum computing, some theoretical way to the some product development phase. So before going to talk about the quantum computing, let's understand the basic computer formalism, means how the computer works. So what happened between the input and output into the computer? So as you can see here in the upper level block, we take the basically input and we are having this some laptop, we give some input to the laptop itself. These laptop will do some kind of computational work, some kind of calculation will be done inside this device or machine. And finally, we'll get some fruitful output, whatever we want as a result from this computer. If you come into the down, this laptop itself has been replaced with the quantum computer, quantum device itself. And in the similar manner, as the traditional computer system takes the input and produce some output, the similar manner, this quantum computer also take the input and produce the output and do some functionalities inside this quantum computer. So there is a lot going inside a computer to keep everything organized. We will break the computer down into the layers that will build on each other. And you will see here, it will start from the basic bit, classical bit, and then afterwards we are going upward direction. It will go layer by layer. Then gates are coming. Then few circuit designing are there. These protocols and algorithms are there, which will take the work from the circuit to perform some computation or operation, and finally will come into the application part. So here, if we'll say the overall, this overall structure is known as the stack. So what is stack? Basically, the stack organizes all the layers of a computer operation, and starting with the most, fundamental and hidden from the side on the bottom. If you'll see, so we will work out our way from the bottom. So classical bit to the top application today. So let's start with the what is bits. See, here I'm going to give you one basic fundamental idea. I'll only talk about the basic classical computers kya hai, how they works basically, and what kind of issues are there with the classical computer. उन issues को हम कैसे quantum computer से overcome कर सकते हैं, वो basic concept लेकर मैं यहाँ पर आया हूँ. बहुत ज़्यादा आपको deep में quantum computer में लेके नहीं जाना चाहता, जिससे कि एक general idea हमें लग जाए. So that's why we can start working on to the quantum computer. So what is bits? So bits are the fundamental unit of the information to the computer. Basically, we have all kind of files. हमारे पास में text file भी होती है, word file है, उनकी size होती है KBs में, MB में. So you can see what is what. These bits are nothing but the huge information which that particular type of files is having. So there is a different ways to represent the bits. Basically, 1 and 0, it is a very common way if we'll talk about in the sense of computer. Some other ways are also there. Some people can understand it as a 1 as a years and 0 as a no itself also. If we'll talk about the switches, then close connected loop or a closed switch is known as the 1 and will represent it as a 1, and this open switch will represent as a 0 itself. So there is a multiple ways through which we can represent the classical bits. Once we'll go upward toward upward direction, so we'll have the gates now. So gate are what? So gate are the manipulators. Basically, gates manipulates the bits. So the fundamental idea is that these bits are nothing but some electrical pulses, electrical signals, and these electrical signals in the atomic level, they goes inside some computer device or some electronic device, and finally we get some kind of output after performing some computational operation over here. So they allow us to turn the simple input into the simple output basically. So if we go more towards upwards, so then what is circuit basically? The circuit is a sequence of gates. So what also see here we can have a AND gate, OR gate, NOR gate, NAND gate. Means a lot of gates are there, and see once we'll combine all these gates together, then we basically we create some kind of circuit. So circuit is a sequence of gates, and by combining many different gates in the certain order, we can start to process input into the output in a more complex and interesting ways basically. And most fundamental, if we'll see, or a great example of the circuit, if we'll see, so the classical example of the circuit is one of the that can be added two numbers, that is known as the full adder. You might be aware with this full adder because in a first year itself in a digital communication subject, we basically have this particular kind of full adder to understand. So what it does basically, it takes the two input, and after giving these two input to the this particular kind of circuit, and through different gates it is going to be passed out, and finally we are getting the addition value of these two different values A and B. Upward once again, then here we'll have the some classical algorithm and protocol. So if you see here in a circuit, what we basically have, we have some kind of computation. So how this circuit will perform the computation, that is with the help of these algorithms. So these algorithms and protocol give the instruction to the circuitry to perform some computational operations. So algorithm and protocol are the agreed upon steps computer used to solve the problems, and these are how application perform their task through the search algorithm. Different Google search algorithm, all these are popular algorithms are there, protocols are there through which these circuits basically perform the task. Finally, if we'll come into the application part, so application are what you see are the use, for the example, like different application runs in your computer. As a as a user, you people interact with the application basically. And here, like just like each and every person have interacted with this Google. Sometimes you search for some data. So if you type the quantum computer into the Google, so you'll get some kind some group of photos which will come related to the quantum computer itself. So these are the different applications which comes into the top layer of the basic computer. So here we talked about the basic computer terminology. So what is the problem? My question is, what is the problem? If we have a classical computer and it is working perfectly, all these kind of tasks are happening in a proper way. All these layers are there, each layers have their own task. Then what is the problem? So let's go and talk about what is the problem basically. So if we'll talk about the problem with the classical stack, so the thing is that the reality is that classical computers are getting so powerful. Nowadays, the computer is so powerful, even though they are hitting the physical limit caused by the nature. So they are, the computing power of the computer is going to day by day, it is going to be increased. High computational power computers we have a supercomputer nowadays. So in 2005, Gordon Moore said that in terms of size of bits, you can see that we are approaching the size of atoms. Atoms, it means what we are going, means we are decreasing the size of the devices basically. Earlier we were having a computer, then we were having a laptop, then we have a pumped up and on all those kind of. So see basically what happening, as the day by day we are increasing, means the technology is going to be grow, the device size are going to be decreased, come into the size of the atoms, which is a fundamental barrier. Basically we have another 10 or 20 years before we reach a fundamental limits. So Gordon Moore, he's a co-founder of the Intel, we can say a grandfather of everything whatever we have in the field of computer right now. So in 1960, Morse predicted that we would be able to double the power of computers every 2 years. And that was the predictions. We call it as a Moore's law. So it is not a kind of law, basically. It is a kind of suggestion or prediction which has been given by the Morse. And that's why this particular prediction, we call it as a Moore's law. So, and here you can see that he has predicted in 1960. And right now, if you'll see, that is a data from the Our World in Data. That is a very well known and popular website, authentic website, through which we can believe on this particular data, whatever they are providing. So you can see the number of transistors per microprocessor. It means that the size of the transistor are going to be decreased day by day, and the number of transistor per microprocessor is going to be increased. You can see, and it is going to be proved that whatever Morse said in the 1960. So squeezing the more power into the computer means what? Actually, we are means increasing the computing power of computers. So what do we mean by this? Basically, it means that the transistors are going to be smaller and closer together. So basically, transistors are going to be smaller and closer together. It means the number of bits are going to be increased. So a few of the articles, it is going to be support to our statement that here you can see that the transistor made using two automatically thin material sets size records. IBM having a 2 nanometer chips having a transistor. If I'll give you some example, 2 nanometer, what is it means? What is the size of this particular transistor? You can see, you can understand by with this example. To understand this, you can see a human hair is having a 50,000 to the 1 lakh nanometer thin, thick basically. This is our human hair I'm talking about. And you can understand that 2 nanometer, how small it is. Even though our fingernails are going to grow about to 1 nanometer per second, means every couple of seconds we are having a new transistor. So that kind of revolution is going to be made into the field of computers or in the field of computation. But what happening as the day by day we are reducing the size of transistor, we are and we are increasing the computational power. After a certain size, quantum effect being a cause of a problem because of this quantum physics. If you have gone through earlier, so because of this reason, certain size quantum effect begin a cause of a problem. So let's understand what kind of problem we face basically. So our example of quantum effect causing a problem is here it is a quantum tunneling. So I'm going to discuss this problem means in a quantum mechanics. That is what quantum tunneling, and object can teleport to the other side of a closed barrier without ever touching it. It means here you can say that if it is an atom, this one is a barrier. So quantum tunneling phenomena, it says under the quantum mechanics that that particular atom will pass out this particular barrier without touching it, even though. Let's suppose that this barrier I'm putting here, that quantum should not cross this barrier. But due to this effect, what happens? This quantum is going to be, this atom is going to be, teleport from the other side. That is the thing. That is the quantum tunneling. So if this happening, the question comes, why this particular quantum tunneling is a problem for the classical computation? Okay, that thing is happening, no issue. But why this is a challenge? Why this is a problem for classical computing? That question comes in our mind. So if it is there, let's try to find out the answer of this question. Here you can see that we are talking about the transistor. So what are the transistor? Transistor basically act as a electric switches, meaning electricity is stopped by the transistor being off. So basically this is a barrier here. And under this, these are the atoms. These are the electrical atoms. So and they are passing through this particular tunnel. Here we have the switches. So this is a switch on condition wherever in that particular point of time, these atoms are flowing towards this tunnel. And here we have a switch off, means now we are going to switch off this particular tunnel. So now here we have created one barrier. So this power will not go transmit from the, means these atoms will not transmit from this particular place to this particular place. It means the power electricity will be switched off or something like that. We can say that the fan is switched off right now. So this is a common phenomenon of transistor. Now, what is the issue? If suppose that this particular tunneling effect will apply, it means we are going to reduce the size of the computer. So definitely at the particular moment of time, that tunneling effect will come into this transistor itself. So what would be happen? Electricity is made of the quantum object electron that can tunnel through barriers. Okay, of course, that things are happening here. But the thing is that because of this reason, so electricity could appear on the other side of the transistor. Because see, what tunneling effect says that this quantum can pass out this barrier without touching it, it can go outside of it. So if that tunneling effect will apply over here, so that barrier will might be possible, it will not stop this atom, and this atom will come out of this here. So what would be happen? This could cause zeros to look like ones and create errors in our calculation if this particular atom will come here. So the thing is that quantum effect, like tunneling, cause classical computer work incorrectly. At particular moment of time, when we are reducing the size up to the quantum level, a particular time will come in that way. On that time, this classical computer work incorrectly. The result will come, wrong result you will get from the computer itself. So meaning we cannot continue making classical computers more powerful for more long. This is the end of the Moore's law, basically. Means there is a certain limit, means afterwards we cannot go down and down and down, and once again we cannot continuously, we can decrease the size of the transistors, and by this way. Okay, so let's go ahead. So instead of trying, see, so this is the issue there in front of us. So do not try to fight with all those things. We just try to find out the solution, how we can means utilize this kind of concept if it is happening. So how we can utilize this concept to develop some high computational power computer. So instead of trying to fight these quantum behaviors, let's use them. Now here the quantum stack comes into the picture. If you'll see here, the quantum stack looks similar to the classical stack, but uses quantum mechanics. So everything, whatever it was the classical earlier, now it is a quantum. So this one, classical bits are converting into the quantum bits, and we can call it as a qubits itself. Quantum gates we are having, quantum circuits we are having a quantum algorithms and protocol. It is not necessary it is a quantum application. It might be possible just like we have some intermediate between the high level language and the low level language. We can having some intermediate, some tools, devices, or some software here also. So application might be possible. It is not quantum. It also be possible. These are the quantum. Right now we are more focused towards this lower part. So qubit, gates, and measurements together make up the quantum circuit. So these three things comes together, then we call it as a quantum circuit. And we are more focused today on the bottom of the stack itself. So let's begin with the qubit. So here we have the quantum bits. So what is quantum bits? A qubit is a quantum bit. It is a fundamental unit of the quantum information and can be in the 0 and 1 state or a superposition. So here you can see that the bit is not only in a zeroth or first condition, it means 0 or 1. These are the two different states basically. So qubit will not only be in a 0 state either or in a 1 state, it also can be in between 0 or 1. And this particular situation is known as the superposition. It might be possible right now, this superposition is not clear to you all, but in a next slides, I'm having some examples. So that's why you can understand what do you mean by this superposition. So basically qubit is having a more than two states, 0, 1, and one more state is here that is in between 0 and 1. Now, let's understand what is the difference between the classical and quantum bits. So, unlike the classical bits, qubit demonstrate quantum behavior like being able to be in a superposition of 0 or 1, as I said. So here if you'll see, this is a classical bit. So classical bit can be 1 or 2 states, only 0 or 1. Either it would be in a 0 or it can be in a 1 state. So whenever you will perform some task, so you will get the result either 0 or 1. But here in qubits, if we'll talk about, qubit can be in a 0, 1 or in a combination of these two states. Bloch sphere is there. I'm not talking about the Bloch sphere right now in today's talk. because it is some different concept. Whenever we'll talk about the algebra and all, then we can think about it. But later, right now, I can say that we have a state 0, 1, even though we have a few states in between 0 and 1, and that kind of bit is known as the qubit itself. Okay, so going in a more depth and little bit try to understand the need of the quantum computer. अभी तक हमने सारी चीजें पढ़ी, क्लासिकल कंप्यूटर में क्या स्टैक्स होते हैं, स्टैक लेयर्स होती हैं, क्वांटम कंप्यूटर में क्या होती हैं। अब अपन थोड़ा सा समझने की कोशिश करते हैं कि आखिर क्वांटम कंप्यूटर की जरूरत क्या है, क्या जरूरत पड़ी, क्या कि ठीक है, टनलिंग इफेक्ट से प्रॉब्लम हो रही थी, हम ज्यादा छोटा नहीं कर पा रहे थे डिवाइसेस को, लेकिन व्हाट इज द रीजन बिहाइंड टू यूज इट? सो लेट्स ट्राई टू अंडरस्टैंड नाउ द फ्लिपिंग ऑफ अ कॉइन। आई एम टेकिंग वन एग्जांपल एनालॉजी। So we can think of a qubit like tossing a coin. हम एक कॉइन को टॉस कर रहे हैं, तो इधर विल गेट दी हेड और जीरो। सो फ्लिपिंग इन द एयर लाइक जब हम उसको फ्लिप कर रहे हैं, सो बिटवीन वेन एवर द कॉइन इज देयर एट अवर हैंड, इवन दो जब हम फ्लिप करने से पहले भी कॉइन हमारे हैंड पे होगा, और फ्लिप करने के बाद में जब ये कॉइन वापस रिटर्न होगा तो भी हमारे हैंड में होगा, दैट इज ईदर जीरो और वन कंडीशन, हेड और टेल वी विल गेट। बट इन बिटवीन ऑफ दीज थ्री कंडीशंस, व्हाटएवर योर सिचुएशंस यू आर लुकिंग हियर, दैट इज सुपरपोजिशन बेसिकली। इट मींस हमारा जो कॉइन है यहाँ पे, ये 0 और 1 के बीच में रोटेट हो रहा है, डिफरेंट डिफरेंट स्टेट्स में रोटेट हो रहा है, दैट इज नोन एज द सुपरपोजिशन बेसिकली। So flipping in the air is like a superposition. We don't know if it is a both 0 or 1 until we force it to the stop flipping. जब तक हम इसको रोकेंगे नहीं, तब तक हमें नहीं पता होगा कि हमारा जो आंसर है either it is 0 or 1. So hope you understand this phenomena. So once we catch the coin and look at it, it collapses to either head 1 or tail 0. If you want to know the probability, if you want to know the probability of seeing heads versus tail, then we have to try flipping to the coin many times basically. So if we're 2-3 times or 5 times, it will repeat this flipping, and then once we record this observation, what result we are getting, then we can calculate the probability of getting head or tail basically. So here you can see that I have taken the coin and then afterwards flipped it out, and then we got some result and entered into this, record this particular result into this table here. And if we'll repeat this process again and again, then we can have a set of observation. Now, I'm going to stop it here, and I'm going to tell you the one phenomena. See, here you can see in the results, 50% of probability is there to get the head, or 50% probability to get the tail itself. But it is not the correct thing, because see, if you'll do repeat this observation 1,000 number of time, might be possible. You will get many number of times heads, less number of time tails. You can have a many number of tails, you can have a less number of heads. You can also have the 50% of time heads, you can also have the 50% of tails. It means it is not necessary that 50% of time you will get the head or tail. Sometimes if we'll talk about the probability, in that sense, we can say that if we don't know exactly how many number of times head and tail will come, so we can say that yes, okay, there is a 50% of probability that head will come or a tail will come. But मेरा कहने का मतलब ये है कि यहाँ ये जरूरी नहीं है कि you will get the 50% of head or 50% tail. It is depend on the number of flipping, and different number of times you will get the different number of result, or different type of result also. So what we are going to take away, we are simply can we know what state it will be in until we force it to the stop spinning. हम जब तक इसको रोकेंगे नहीं, तब तक हम ये नहीं कह सकते हैं कि जो हमारा कॉइन है वो किस पर्टिकुलर स्टेट में है। लेकिन यहाँ एक फिनोमिना है, अगर हम इस क्लासिकल कंप्यूटर के सेंस में समझें, तो अगर हमें ये पता है कि कॉइन कैसा है, यानी कॉइन का क्वालिटी क्या है, किस मटेरियल से बना है, एयर कंडीशन क्या है राइट नाउ, कितने प्रेशर से हम कॉइन को उछाल रहे हैं, और ये कुछ ऐसे पैरामीटर्स अगर हमें इनका एक्यूरेटली पता है, तो हम आसानी से पहले से प्रिडिक्ट कर सकते हैं कि अगर मैं इस कॉइन को फ्लिप करूंगा तो मेरा रिजल्ट क्या आएगा, कि हेड आएगा कि टेल आएगा। कुछ मैथमेटिकल हमें फॉर्मूलाज लगाने पड़ेंगे, कुछ पैरामीटर्स लेने पड़ेंगे, और इसलिए विद द हेल्प ऑफ मशीन लर्निंग एंड ऑल दोस काइंड ऑफ स्टफ्स आर देयर, स्टैटिस्टिक्स आर देयर, हम आसानी से पता कर सकते हैं कि ये हम कॉइन को उछालने के बाद में इसका रिजल्ट क्या होगा। लेकिन जब हम बात करें, दिस इज नॉट ट्रू इन द इफ विल टॉक अबाउट क्वांटम मैकेनिक्स, इट इज नॉट ट्रू इन दैट केस। ये क्लासिकल कंप्यूटिंग केस में तो पॉसिबल है कि हमें ये पता हो सकता है पहले से कि इसमें हेड आएगा या टेल आएगा, लेकिन हम क्वांटम मैकेनिक्स की बात करें तो उसमें ये ट्रू नहीं है। तो चलिए, लेट्स डू द सेम एक्सपेरिमेंट, बट नाउ विद द क्यूबिट्स वी विल ट्राई टू परफॉर्म। सो हियर let's understand the superposition with the help of qubit experiment. So here we have a one qubit, start with the 0. And now if we'll here once we'll what we can do, अगर हम यहाँ पे कॉइन और कॉइन को हम फ्लिप कर रहे हैं तो हमारा जो कॉइन होगा वो सुपर पोजिशन में होगा, इक्वल सुपर पोजिशन में, यानी कि यहाँ सिमिलर प्रोबेबिलिटी है, इक्वल प्रोबेबिलिटी है कि वो 0 स्टेट में हो, इक्वल प्रोबेबिलिटी है कि 1 स्टेट में हो। एंड लेकिन ये हम तब तक नहीं बता सकते हैं जब वो कॉइन हमारे हाथ में वापस लौटेगा, तभी हम बता सकते हैं कि वो हेड आया या टेल आया। सिमिलरली अगर हम क्वांटम कंप्यूटर की बात करते हैं तो अगर इनिशियली हमारा जो क्वांटम है वो 0 स्टेट में है, then if we are we are applying some operation on that particular quantum atom, then that particular quantum will be in a superposition. It means might be possible कि ये 0 1 किसी भी स्टेट में हो सकता है, लेकिन once we'll apply this measurement in that, we can easily say that we will get either 1 or 0. So here you can see that after performing this experiment, you can record this measurement. Here we are getting 1. And similarly, if we'll repeat this step again and again, we can have this kind of results. अब यहाँ पे मैं पिछले एग्जाम्पल से इस एग्जाम्पल को कंपेयर करूं तो यहाँ पे इस बात की ये गारंटी होगी कि हमारा जो 0 है वो 50% ऑफ टाइम ही आएंगे और 50% ऑफ टाइम 1 आएगा। बेसिकली हम जब इस पे मेजरमेंट अप्लाई करते हैं तो दैट इज व्हाट कि हमें या तो 0 आएगा या तो 1 आएगा, और एंड द थिंग इज दैट कि इट इज अ गारंटीड दैट कि 50% ऑफ टाइम 1 आएगा और 50% ऑफ टाइम 0 आएगा। बिकॉज ऑफ दिस हियर वी आर गेटिंग सेम। अगर मैं पिछले वाले से कंपेयर करूं तो हमें ये तब तक नहीं पता चलेगा जब तक हम मेजरमेंट ना परफॉर्म करें, यानी जब तक कॉइन हमारे हाथ में वापस ना आए तब तक हम नहीं कह सकते कि हम 0 स्टेट में या 1 स्टेट में। इट मींस वी नीड टू परफॉर्म द मेजरमेंट हियर। बट जैसा कि हमें पिछले एग्जाम्पल में क्लासिकल कंप्यूटिंग एग्जाम्पल पे जब हम देख रहे थे कि वहां पे हम जब क्वाइन को अगर हमें क्वाइन की कंडीशन के बारे में पता है कि क्वाइन किस मटेरियल से बना है, एयर प्रेशर कितना है, कितने फोर्स से हम क्वाइन को उछाल रहे हैं, ये कुछ हमें पैरामीटर्स अगर पता है तो हम आसानी से कह सकते थे कि क्वाइन में हेड आएगा या टेल आएगा। But whenever we are talking about in the sense of quantum computer, but unlike the coin, there is nothing we could do to know what state it will be in a beforehand. हम ये पता ही नहीं कर सकते हैं जब तक हम मेजरमेंट अप्लाई ना करें सुपर पोजिशन में, तब तक हम ये पता नहीं कर सकते हैं कि हमारी स्टेट 1 होगी या 0 होगी। यानी कि क्वांटम मैकेनिक्स ट्रूली रैंडम है। ट्रूली रैंडम इट मींस व्हाट कि जब हमारा जो क्वांटम है अगर वो सुपर पोजिशन पे है, जब हम उसमें मेजरमेंट अप्लाई करेंगे तो इट माइट बी आल्सो पॉसिबल कि विल गेट 1, इट माइट आल्सो पॉसिबल विल गेट 0, बट हाँ दैट इज अ गारंटी विल गेट 50% ऑफ टाइम विल गेट 1 और 50% ऑफ टाइम विल गेट 0 बेसिकली। So here, if we'll come into the second level, in next level, that is a quantum gates. So quantum gates basically perform some quantum operation on the qubit to change their state in order to perform the quantum computation. ये gate हमें classical computers में भी मिलते हैं. Similar type of gates are also here. So these quantum gates are nothing but these are the manipulators which are going to use for to manipulate the bits itself. So here we can say that the qubit itself. So quantum gate perform some quantum operation on the qubit to change their state in order to perform the quantum computation. वैसे तो कई सारे गेट हैं, बट आज एग्जांपल के तौर पे मैं केवल x गेट और h गेट की ही बात करता हूँ। तो if we'll see here, the x gate give the opposite of the input, just like a NOT gate, So here X gate gives the opposite of the input. So initial qubit state is 0 and 1, and once we'll apply this input to the, we'll give this X gate, then we'll get the 1 here. And if we are giving the 1 as an input, then we are getting a 0 over here. If we'll see this H gate, so H gate creates the equal superposition basically. And here, if you see 0, if you are giving, then after giving this input, the H gate, we are getting the equal superposition. So it means that particular, input or atom or quantum right now, it would be either in a 0 state or it can also be in a 1 state. And similarly, if we are giving 1 here as a input to the H gate, similarly, this input will also be in the equal superposition. So this is the example. So here we have inserted the 0 qubit and to the H gate, and finally we are getting the output in between the 0 and 1. That means it is there in a superposition itself. तो आई थिंक मैंने कुछ ज्यादा वैसे धीरे धीरे कोशिश की थी ये समझाने की कि आखिर क्वांटम कंप्यूटर्स की जरूरत क्या पड़ी। तो इफ आई कंक्लूड माय टॉक ओवर हियर राइट नाउ, So basically, to increase the computational power of the computer, basically we are looking forward towards the quantum computers. Lot of research is going on. Still, we have to work upon on this. Right now, we are going through with some theoretical content. In future, definitely we'll go through with some product development stage also. Governments are supporting. Lot of funds are going to be, given by the government itself in the field of the quantum computer. So it's all about from the quantum computer side. So from my side, thank you everyone. Now, if you have any query, we can have a one-to-one discussion on this.
थैंक यू सो मच सर। हमारे जो स्टूडेंट हैं वो यूट्यूब से जुड़े हैं हमसे,
जी मैम।
और फैकल्टीज इसी जूम से जुड़े हैं। सर आपका पीपीटी मिल सकता है क्या? ऐसा क्वेरी था एक दो बच्चों
जी
का।
डेफिनेटली मैम, जैसे ही मैं इसको कंप्लीट करूंगा यहाँ से, मैं वैसे ही आपके साथ में शेयर कर दूंगा। और इफ दीज पीपल आर रियली इंटरेस्टेड, तो हम अभी, चूंकि क्या मुझे एक तो समय भी 45 मिनट कुछ बहुत ज्यादा लग नहीं रहा था, तो मैं केवल बेसिक पार्ट पे ही गया। तो इनकेस अगर कभी लगता है तो हम एक और इस पे टॉक रख सकते हैं, जिसमें हम थोड़ा सा एडवांस लेवल पे चल के क्वांटम कॉल बेहतर समझ सके।
हाँ, बच्चों को शायद अच्छा लगा, तो
जी
एक दो बच्चों की मतलब रिक्वेस्ट है ये।
जी जी।
अगेन थैंक यू सो मच सर, यू
थैंक यू
शेयर्ड
सो मच मैम।
knowledge to us. Again, once again, thank you so much.
Thank you ma'am. So with your permission, shall I leave ma'am?
Yes, sir.
Yeah, thank you so much ma'am.